me 1 second. I will start recording now, Jason. Good morning. Good morning, everybody. Welcome for this new colloquium by the Instituto Astrofísica de Andalucía. Today, we will have the talk by Dr. Jason Hessels from the University of Amsterdam and ASTRON. And he will talk about exploring the transient radio sky with SKA and its precursors. So thank you, Jason, for being here. And Isabel Marquez, our scientific director, will make a proper introduction of you. Isabel?
Okay, thank you very much, Rene. Good morning, everybody. Thank you very much for being here again to visit a new one. I mean, a new colloquium from the Observatory program at the Instituto Astrofísica de Andalucía. It's a pleasure for us, as Rene has said, to have today Professor Jason Hessels with us. Thank you very much, Jason, for accepting an invitation that I'd like to, publicly express the extension of the invitation to an in-person one for next October. So thank you very much. Professor Hessels received his PhD in 2007 from McGill University in Canada. And since then, he has been working in the Netherlands, where he's now professor of high energy astrophysics at the University of Amsterdam. And he's also chief astronomer at ASTRON, that is the Netherlands Institute for Radio Astronomy, as you know. His research focuses on the study of pulsars and fast radio bursts. He has studied these phenomena primarily using large radio telescopes, and this research has been funded via a number of grants from the European Research Council and the Dutch Foundation of Scientific Research. Research highlights include the discoveries of the fastest spinning and most massive neutron star, as well as the discovery of the first known repeating fast radio burst source. His research group is currently focused primarily on localizing fast radio bursts to the host galaxies and local environments using a very long baseline interferometry. He is co-chair of the SKA Transient Science Working Group, and he's also the project scientist for the LOFAR 2.0 upgrade to low frequency array. And as Rene said, he's talking today about exploring the transient radio sky with SKA and its precursors. So thanks again, Jason, and the floor is yours.
Great. Thank you very much, Isabel, for the nice introduction. I'll start sharing my screen now. Of course, I'm very much looking forward to seeing you in person at some point. Can I just confirm that you can see my screen?
Yes.
Yes. All right. Great. So indeed, I'm going to be talking about exploring the transient sky using the Square Kilometre Array and its precursors. The way I've structured the talk is I'm first going to talk about the SKA in some broad terms in terms of what we hope to do with transients, and then I'm going to focus. I'm going to go deeper on one of the really exciting science cases for SKA, fast radio bursts. Also, as a means of showing you the kind of the depth of the science that one can do, and also using it as a way of showing kind of the exploration that we're still making of the transient radio sky and what the prospects are for increasing that with the Square Kilometre Array. So first off, let me talk a little bit about the Square Kilometre Array, and especially in the context of transients. I'm going to assume that the vast majority, if not all of the audience, has heard of the Square Kilometre Array. If you haven't, it's going to be a two-site, in terms of telescopes at least, radio telescope, which is going to be preeminent in the world. It's going to be, construction has started already on the SKA, which is very, very exciting. And towards the end of this decade, we will be making observations with the full SKA observatory. And that includes the Square Kilometre Array Mid telescope, which is going to be hosted in South Africa, which is going to be a major extension of what already exists in terms of the Meerkat telescope there in South Africa. As well as, quite importantly, also in Western Australia, the Square Kilometre Array Low Array, which will be providing lower radio frequencies, meter wavelengths, and is a telescope that is going to be an order of magnitude more collecting area than the current LOFAR telescope, the low frequency array that we have in Europe. So this is really going to be a preeminent telescope, and it's not just one telescope, it's two telescopes covering a very broad range of radio frequencies, providing high angular resolution, huge sensitivity. And of course, we want to use that for a wide variety of science cases, and the one that's closest to my heart and associated with the science working group that I lead is, of course, transients. And there's no way that I can do justice to all of these very interesting areas of transient radio astronomy in a single talk. That's why I've chosen to dig deeper into just one of the topics later in the talk. But let me just give you an idea of what the breadth of different scientific topics is. And this list is, of course, also not exhaustive. You've undoubtedly heard of the revolution that is happening in multi-messenger, multi-wavelength astronomy. Radio astronomy plays an important role in following up gravitational wave events, in particular the kilonovae that they can produce. So I have a couple examples here of radio observations, VLBI observations resolving the evolving morphology and position of radio emission associated with the first double neutron star merger, the famous gravitational wave event 1708-17, as well as tracking the afterglow emission of that event. These are really interesting events in terms of understanding the production of heavy elements in our universe. So elements beyond iron. There are elements in the periodic table, quite a few of them, that are predominantly formed, we believe, through this type of process. And really nailing down, what fractions of different types of elements are produced. Using these events as probes of that creation of the periodic table is really very exciting. I'm going to talk about fast radio bursts in much more detail later in the talk, so I'm not going to elaborate on them right now. I'll be explaining what they are as well. One of the things that I think is super exciting for the Square Kilometre Array is really probing relativistic jets from both neutron stars and black holes over a huge range of mass scales. So I'm talking about even stellar mass black holes up to supermassive black holes, of course, and particularly neutron stars, since they also form jets in a almost uncannily similar way to how accreting black holes form jets. They are typically much weaker, but with a much larger telescope like the SKA, I think there's a huge avenue for exploring accretion onto neutron stars and also outflows from neutron stars using the SKA. And I have an example here. This is not a neutron star, this is a black hole, but beautiful work that was done by James Miller-Jones et al., collaborators, looking at a precessing jet from a black hole. And doing this type of work is currently, groundbreaking to be able to do this. I think this is something that will become, routine with the SKA and be able to trace precessing jets of accreting compact objects. Of course, there's a whole variety of different types of supernovae. We have long gamma ray bursts, we have superluminous supernovae. There's a whole zoo now of different types of supernovae, many of which produce detectable radio emission. We'll be able to study those with the huge collecting area of the SKA. The same goes for looking at colliding wind binaries, where, for instance, one might have a neutron star or a black hole with a massive stellar companion, looking, for instance, in this case, at for instance, pulsar wind ramming into the wind of the companion star, creating a shock. We can study particle acceleration in these systems. They're really laboratories for understanding particle acceleration in a way that we can't do in other environments. We can study the radio emission from tidal disruption events, so when stars get too close to a supermassive black hole at the center of their galaxies and get ripped apart, and that stream of material can also create shocks, internal shocks that we can detect in the radio. We can consider flare stars, so magnetically active stars in our own galaxy, like M dwarfs, for instance, very low mass stars, which are incredibly abundant in our galaxy. Like the majority of stars in our galaxy are obviously very low mass stars. And we can use radio as a means for measuring their magnetic fields and also the impact that these stars have on their planetary systems, which is, of course, very interesting for understanding the conditions for habitability in other planetary systems. And perhaps maybe the most exciting thing, although I won't say a lot about it, is of course the unknown. By building a much larger telescope, by probing new parameter space, the prospects for finding unexpected things become very high. I would argue that the SKA, in terms of doing transients with the SKA, can benefit enormously from adding VLBI to the equation as well. And in fact, I gave a talk about this last week at the SKA VLBI conference on behalf of the Transient Science Working Group. And especially, with the mid array, which will be built in South Africa, linking that to the very nice radio telescopes that we have in Europe currently that are part of the European VLBI network, I think this can be scientifically even more powerful if the SKA brings in these long baselines. And that's because, anything that is transient in nature is going to be compact. If it's varying on short timescales, then the size of the emitter cannot be particularly large. And there are so many advantages to just going to the extremes of angular resolution that one can achieve in radio astronomy. And this includes, of course, tracking motions, resolving sources, looking at proper motions. There's great science that you can do with this if we can connect the SKA to the long baselines that we have in Europe. You might be wondering, what kind of frequencies does one want to do this type of science at? And of course, the 5 to 10 gigahertz band, what radio astronomers will call the C and the X band, these are really workhorse frequencies for studying transients, because a lot of transients, given their spectrum and variability timescales, and also, if you want to go to very high angular resolution, these are kind of the best balance in terms of sensitivity and angular resolution that you can achieve. But I would also argue that not only is SKA mid going to be interesting for transients, SKA low has huge prospects for looking at coherent transients. So if you're looking at synchrotron emission from transients, things like jets from accreting sources, obviously I think there are big advantages to going to higher frequencies. But if you're looking at coherent transients, things like pulsars or fast radio bursts, there are a lot of advantages for going towards lower frequencies. Partly because these sources typically have fairly steep spectra, so that they become brighter at lower frequencies, but also because the huge collecting area and huge field of view that SKA low is going to offer opens up a really large parameter space compared to what we can currently probe with our existing telescopes. So think about not only FRBs and pulsars, also think about low frequency emission from flare stars, possibly direct emission from exoplanets as well. Very exciting to go to low frequencies as well as the mid frequencies. One of the things that makes transient science a little bit unique compared to other science cases for SKA is the fact that transients, being on sky at the right time is scientifically really crucial in many cases. So we need a telescope that is really responsive. This is a key technical capability of the telescope, to be able to get on to interesting sources when they're doing interesting things. A great, a premier example of that obviously is, if you have a gravitational wave event, you want to be on source as quickly as possible. You want to figure out exactly where the source is on the sky, and you want to keep monitoring it. This needs to be automated at some level. And what's going to be very interesting in the coming decade is that we're going to have to get really picky and choosy as well, because we're in the regime right now where, to a certain degree, the most interesting transient astrophysical events, they can be followed up in reasonable detail. But we're entering a new regime as a field in the coming decade, with facilities like the LSST, or also known as the Vera Rubin Observatory. We're going to be getting millions of triggers per night, and fishing through those triggers and thinking about what are the most interesting things to be spending telescope time on is a non-trivial exercise in its own right. You want to cast a broad net so you can be surprised about interesting things, but you don't have enough available telescope time on the SKA or any other facility to follow up millions of astrophysical transient events every single day. So this is an interesting challenge for us in the coming decade. Add to this the fact that getting quick observations of interesting astrophysical transients is scientifically important. Getting on source quickly is in many cases quite valuable. But at the same time, monitoring sources, continuing to look at them after they've had an outburst, or of course there are many types of sources that have periods of activity and quiescence. You want to track these things, and having high cadence observations, so doing regular monitoring, ideally in a way that is agnostic about what the source is doing, just have a regular cadence of monitoring, because you might be surprised by the source becoming more active or less active at certain times. This also becomes critical. And this is a challenge for telescopes like the SKA, because you want to be doing wide field deep surveys for a variety of different science cases, but you also want to be going back to certain targets over and over again and monitoring their flux density, their polarimetry, their spectrum as a function of time. And this is why in our science case, sometimes we're not limited by the sensitivity of the telescope. So for certain types of applications, the SKA is too large a telescope, and then you have to start thinking of creative ways in which you can split off parts of the telescope. You can take subarrays of the telescope, for instance, 10 dishes from the telescope that are constantly monitoring interesting sources that have active periods and that are bright enough that you can see with a very small subset of the telescope. But the interesting science comes from the fact that you're looking at them at a very high cadence. And I'll give you a very nice example of that later in the talk as well, where sensitivity is not the key limitation. It's more how often can you be looking at these sources. So in terms of observing strategy, I think it's clear that both SKA mid and SKA low, through the surveys that they're going to be doing for other science cases, continuum surveys to map the sky, polarimetric surveys, H1 surveys to map the gas and other galaxies. We as a transients community, we want to be piggybacking on all of those observations. We want to use all of those observations to discover new transients in SKA data and then trigger internally on those new discoveries to do follow-up observations. I think we want to do this not only using the capability of the telescope to make very deep, high angular resolution images of the sky, but the SKA is also being developed to be a telescope that provides very high time resolution for surveys of pulsars and also to search for fast radio bursts. The telescope is going to offer also a very high resolution in the temporal domain as well. And we want to, follow up on radio flashes that we detect in pulsar surveys and fast radio burst surveys, make images of those areas to see, what is going on in that region of the sky. Maybe we can find, the afterglow of a long gamma ray burst, for instance, or maybe we can find radio emission from a host galaxy, radio emission due to star formation where the source is found. And of course, also react, as I've said already, to these huge numbers of very interesting triggers that are going to be coming from telescopes like the Vera-Rubin Observatory in the coming decade. So this is kind of like a broad stroke vision of what the SKA is going to mean in terms of transient science and some of the maybe atypical ways in which I think the transient astronomers are going to want to use the SKA. Again, we think of the SKA not only as a monolithic collecting area, we think of it as, a set of collecting area that can be used in flexible ways in which we can use maybe subsets of the collecting area to do high cadence observations. And also as a telescope that needs to respond quickly. If this is a science area that you're working in already and you're interested in joining the Square Kilometre Array Transient Science Working Group, very much encourage you to do so. Even if you're only interested in maybe starting to do transient radio astronomy or transient multi-wavelength astronomy, you're also very much welcome to join the group. The group is currently chaired by myself and Patrick Wout. So just send us an email if you would like to join the group, and we would be very much happy to have you. So after that kind of general setting of the stage, I want to dig deep on one of the scientific topics that I think is going to be very interesting for the SKA, so that you get a bit more exposure to why this science is so interesting and also what kind of impact the SKA can have in this area. So I'm going to talk in depth about fast radio bursts, and given that I'm assuming the audience is fairly broad, I'm going to first motivate what fast radio bursts actually are and give some context for this. So I would assume that a lot of people on the call have probably heard of the Lorimer Burst. This is really, in my mind, a seminal moment in transient astronomy. It's not so often that astronomers discover, a new type of astrophysical phenomenon, and Lorimer burst really is quite a new and surprising thing. So it was discovered in 2000. Also looking for single pulses, and what they found was a single burst. Which is now called the Lorimer Burst. And what you can see here, this is like a spectrogram, or sometimes also known as a dynamic spectrum of this burst. You can see radio frequency here on the y-axis. So it's, the range of radio frequencies that were recorded by by the receiver in the back end. And you can see time on the x-axis. And you can see that this radio signal arrived at different times at different radio frequencies. This is due to dispersion. This is a well-known effect in ionized material, that the speed of light is frequency dependent. So you can see this sweep here. The same thing happens for all of the pulsars that we see in our own galaxy. And if you correct for this sweep, so if you were to move back into the reference frame of the source, removing this sweep, and add all of the frequency channels together, that's what this inset is showing you. It's showing you what the broadband signal looks like. And this burst lasted only for a few milliseconds or so. And as I said, this type of burst, this is very similar to the single pulses that we see from radio pulsars in our own galaxy. So in that sense, it might not at first glance seem that peculiar. But what is very peculiar about the Lorimer Burst, and which caught people's interest very quickly, was the fact that the amount of delay that we would expect, knowing how much ionized material is between stars in our own galaxy, this delay would be maximally about this amount from our entire Milky Way galaxy. So if this source was within the Milky Way, we would expect that at most, if it was at the edge of the Milky Way, we would see a dispersive delay of about 50 milliseconds or so. And the actual delay that we see is about 11 times larger. So there's much larger dispersive delay than we would expect given the ionized material in our own galaxy. And this extra dispersive delay, it was attributed to, and we now know correctly, to extra dispersion, not just from our own Milky Way galaxy, but from the intergalactic medium itself. So the idea was, and this was postulated at the time of the discovery of the Lorimer Burst, that this source was actually located in a distant galaxy at a significant redshift, and that this extra dispersive delay was coming from the ionized material between galaxies, the intergalactic medium. And we now know that this is true. At the time, it was a very bold idea, because why was it such a bold idea to say, well, maybe we can see radio flashes from other galaxies? If we compare this to the radio flashes that we've seen from pulsars, the luminosities that we're talking about in terms of fast radio bursts are insanely larger than those from pulsars. So this diagram that you're looking at right now, this is a phase space diagram where on the x-axis we're looking at the duration of a radio transient. And you can see, a whole variety of different types of radio transients. We can talk about the afterglows from supernovae and gravitational wave events. We can talk about magnetized cataclysmic variables. We can talk about flare stars or solar bursts. They have much longer timescales than pulsars. Pulsars have timescales of a few milliseconds or so. That's how long their pulses last typically. And then on the y-axis, we have luminosity. And what you can see is pulsars have, characteristic timescale of a few milliseconds, and they have some characteristic luminosity, meaning that we can predominantly only see them from our own galaxy. Knowing the distances to fast radio bursts, we can see that they're factors of about 10 to the 12 more luminous than pulsars. So they have similar timescales, the pulses look similar, but given their distances, they are insanely more luminous than pulsars. And this seemed, at the time, really quite shocking. How could this be that there are these radio bursts that are 10 to the 12 times more luminous than pulsars? And we now know this to be true. The field has gotten a lot of interest within the astrophysics community because it's a new phenomenon. It's very exciting to study a new phenomenon. I would say that the field has also captured the public's imagination as well, because if, for instance, if you search on Spotify for the term fast radio burst, you can actually see that there are a number of bands and songs that are named fast radio burst. This is actually an album cover for some band where this is a plot that I made for one of our papers that ended up as an album cover apparently. And there's also this song by this band called Fast Radio Burst as well. There's another band called the Lorimer Burst. It's kind of funny to see. So let me share some shocking facts about fast radio bursts just to kind of motivate why these are so surprising and cool to study. So I mentioned that they only last for a few milliseconds. To put that into context, what is a millisecond? It's kind of hard to imagine what a millisecond is. Well, a millisecond is actually 100 times shorter than the blink of an eye. So these are really ephemeral short duration bursts. We now know that they were created long, long ago in galaxies far, far away. They're at distances of, in some cases, billions and billions of light years. So they really are cosmological signals. And the amount of energy that they pack, given that they're coming from so far away and we can still detect them with our current radio telescopes, it means that that millisecond duration burst, that's carrying as much energy as the sun emits in one day, right? So these are very, very energetic events. Not nearly as energetic as the supernova. I don't mean to give that impression, but for radio phenomena, these are really quite spectacular. And of course, one of the big problems is, or one of the big scientific questions is what is producing these radio bursts? And I would say that although we have some good indications that at least a large fraction of FRBs are related to magnetar emission, where magnetars are neutron stars that are so highly magnetized that their energy output is predominantly resulting from the decay of their really, really large magnetic fields. And we're talking about magnetic fields that are about 10 to the 15 times the magnetic field of the sun. So we think that magnetars, which have a picture at the top here, we think that magnetars are probably a very interesting candidate for explaining fast radio bursts, or some fraction of fast radio bursts. But we, at the same time, have really quite a bit of evidence that maybe that's not the only solution, and that we're maybe actually, with the fast radio bursts that we've currently detected, seeing emission from a variety of different types of astrophysical sources. And this slide is kind of summarizing some of the theories that are out there, some of them more plausible than others, some of them a little bit silly, of course, as well. But there's a large theory space for what FRBs could be coming from. And I think a lot of those theories are actually quite plausible. And given that we're opening such a large new parameter space, I think there's no reason to think that FRBs are all coming from a single type of astrophysical source. I think there's reason to think that by opening this new parameter space, we're actually discovering a number of different types of phenomena at the same time. So that's quite nice. You find a new type of mysterious signal, you want to figure out how it's being produced. That is an interesting scientific question in its own right. Maybe it'll be solved one day, maybe it won't. But regardless of knowing whether fast radio bursts come from magnetars or from a variety of different types of sources, maybe we'll never know. What we do know, though, is that these radio bursts are, again, influenced by the material between us and the source. And not just the ionized material, but also the magnetic field as well. So compared to, say, gamma ray bursts, which we can also see from cosmological distances, radio waves are a lot more delicate than gamma ray photons, right? They're easily influenced by the intervening material and magnetic field. And that means that, for instance, this dispersion effect that I explained to you earlier on, this allows us to measure the total electron column density along the line of sight. So it's a way of kind of weighing the universe. And one of the key scientific goals for the Square Kilometre Array is to use fast radio bursts to weigh the universe, to detect the otherwise invisible baryons between galaxies, which is quite important for understanding the formation of structure in the universe. We can see effects due to how that material is distributed, so how clumpy the material is along the line of sight. So whereas dispersion gives us the total electron column density, effects like scintillation and scattering tell us how it's distributed along the line of sight, whether it's in clumps or whether it's homogeneous along the line of sight. And effects like Faraday rotation, because we can also measure polarization in these radio bursts, they allow us to measure the line of sight magnetic field. So we can measure the magnetic fields and halos of galaxies and in the intergalactic medium. And we know that magnetism has a key role also in structure formation in the universe. So really, every fast radio burst that we detect, we're here somewhere in the Milky Way. This burst is happening in some host galaxy very far away. It is being influenced by the interstellar medium and the circumgalactic medium of that host galaxy. It's being influenced by the intergalactic medium, by maybe the circumgalactic medium of a galaxy that happens to be along the line of sight. And it's also probing the halo of our own galaxy and the interstellar medium of our own galaxy. So FRBs are really fantastic. They're unique probes of the intervening medium, which is otherwise inaccessible to us, otherwise invisible to other types of observations. And what's also great is that fast radio bursts are really quite abundant. And there's now thousands that are known. The all-sky rate is really quite astounding. So we think that there are thousands of fast radio bursts happening somewhere on the sky every single day. So you can probably immediately come to the conclusion that, well, that must mean that radio telescopes have very small fields of view. If we've only found a few thousand, if there's thousands happening every day, that's because we're only scanning very small fractions of the sky at any given time. And again, radio astronomy, one of the great growth areas for radio astronomy in the coming decade is by expanding fields of view to detect rarer types of phenomena. And I think especially SKA low, its huge field of view is going to make huge gains there by being able to cast a broad net over a very wide range of sky. We're going to be detecting things where the limitation is how often those things happen, as opposed to how big the telescope needs to be. So in the last years, one of the main developments in the fast radio burst field has been the detection of a repeating fast radio burst source. So this was discovered with the Arecibo telescope, which unfortunately, I'm sure many people know, the platform of the Arecibo telescope collapsed, and that is very sad. And it's really a shame that the instrument was still such a cutting edge instrument. It's really a shame to see what has happened to the telescope in the last year and a half. But in happier times, Arecibo laid claim to this really quite important discovery, I think, the discovery of the first known repeating fast radio burst source. And it's not so often in science that you have an observation which so clearly differentiates between certain classes of theory, because I would say at the time of the discovery of this repeating source, a lot of the theories around fast radio bursts were invoking cataclysmic events, one-time only explosions like neutron stars smashing into each other or supernova as being the origins of fast radio bursts. And that could be true for some fraction of fast radio bursts, but for any source that's repeating, it cannot be a one-time only event, right? So we know that there's a class of repeating fast radio bursts that must come from some kind of energy source that can sustain its activity for at least years. And this is one of the reasons why we think magnetars are potentially an important part of solving the FRB puzzle. Now, to use FRBs as probes and also to really nail down what the energetics are actually like, and also to figure out what kind of environments they occur in, obviously you want to localize them very precisely. You want to figure out what direction on the sky they're coming from, and you want to then associate them with the host galaxy, where you can get, for instance, the redshift of the host galaxy. And this is another area of radio astronomy which is really quite interesting, I think, in the sense that radio astronomy is a fantastic technique for localizing sources very precisely, using long baselines and using interferometry. And to put the problem into context, if you detect a fast radio burst with a telescope like Arecibo, the field of view of a single dish telescope like Arecibo, there are many potential candidate galaxies within that type of field of view of a few arc minutes or so. And you really need to localize FRBs down to the arc second level, or potentially even better than an arc second precision, to really nail down unambiguously which galaxy they're coming from. So you need a radio interferometer to do that. So I'll talk about that in a little bit more detail in some of the coming slides, but the first time that this was done was for this repeating source, right? Where Arecibo made the detection of the source, then using the VLA interferometer, it was possible to localize some of the sources on the sky to arc second precision, using very long baseline interferometry. So using the telescopes we have here in Europe, which span longer baselines, we were able to localize the source to milli-arc second precision. And knowing that position on the sky very precisely, then you can look in that same direction with large optical telescopes like Gemini in this case. You can detect the host galaxy, you can measure its spectrum, you can get the redshift, and you can know in an independent way what the actual distance to the source is. And then you can take this even farther, right? You can try and match the milli-arc second resolution that's possible with radio astronomy with the best possible optical observations. At the time, that was the Hubble Space Telescope, which in this case found that this fast radio burst is localized to a dwarf galaxy where there is ongoing star formation, and the FRB seems to be right on top of that ongoing star formation, suggesting that it's a young source, which maybe comes as little surprise that it would be some young energetic source. But this is, again, something that the SKA is going to be able to do in one package, right? Because the SKA is going to be doing these wide field searches at high time resolution, which are capable of detecting fast radio bursts. But then at the same time, it provides the angular resolution, sufficient, angular resolution given the long-ish baselines of the telescope, that it will be possible to pinpoint where these signals are coming from, and to match that with multi-wavelength data to figure out the host galaxy, to study the local environment, etc. Yeah, and again, one of the cool things about these sources and about radio astronomy is that radio waves, again, are so sensitive to everything along line of sight. One of the nice things about the source is we could also measure Faraday rotation, so that's the rotation of the linear polarization angle of the signal as a function of frequency, and basically measure the magnetic field in the local environment of the source and show that it's potentially in a very dense nebula. Again, consistent with the idea that it's in the star-forming region and it's a very young source. Now, localizing FRBs has really made huge strides in the last few years. There are now interferometers that are not just following up repeating sources; they're detecting and they're localizing fast radio bursts in kind of near real time. And again, this is something that the SKA is going to do in spades when it is available. And this has shown us we've now localized about 20 FRBs quite precisely to their host galaxies. And I would not say that this has solved the mystery of what FRBs are. It's actually shown us that FRBs seem to occur in quite a broad range of environments. And I'll show you a very striking example in a few slides. But in doing so, we found FRBs in a variety of different types of environments. And again, this, I think, in my mind, this is consistent with the idea that actually in trying to solve the puzzle of what's producing FRBs, we're starting to realize that maybe there's not just one answer to that question, right? So I am cognizant of the time. I would like to finish in the next 10-ish minutes or so. I'd like to show you some of the most recent results that we've been doing here in the Netherlands in our research group that we call AstroFlash. I'm not going to present all of the stuff that we've been working on recently, but I am going to show a few highlights because I think they're also very nicely illustrative of what's going to be possible with the SKA. The first is, localizing the positions of fast radio bursts, again, to milli-arcsecond precision, which is really quite phenomenal. We're currently doing this by playing on the strengths of the CHIME telescope, which is really the world's best discovery machine for fast radio bursts. This is a very wide field telescope in Canada where it's possible to discover a few fast radio burst sources every single day because the field of view of the telescope is so large. It's about 200 square degrees, which compared to a typical radio telescope is a factor of 1,000 larger than the field of view of a typical telescope. So CHIME is finding a lot of FRBs, but CHIME, because in its current configuration is just a single kind of like a single dish telescope, the angular resolution is still quite limited. We've been taking the sources that are known to repeat, and we've been doing follow-up observations using what I would argue is the world's most precise FRB localization machine, and that's currently the European VLBI network. So this allows us to refine the positions of repeating fast radio burst sources by factors of 1 billion in terms of the sky area that we can constrain them to. So zooming in on these positions, for instance, we've done this for a CHIME FRB source where we zoom in and we find the host galaxy, this beautiful kind of face-on spiral galaxy at a distance, luminosity distance of about 150 megaparsecs. And not only do we identify the host galaxy, but we really pinpoint where within the host galaxy where the source is. So with follow-up observations with the Hubble Space Telescope, you can again see this galaxy. It's now, crisper image because this is space-based optical observations. But it's possible in radio astronomy to measure these positions so precisely that we can see that this source of fast radio bursts is very close to a region of active star formation, which has recently actually been argued to have been created, this local star forming activity by a minor merger in the past. And we can see that the source is quite close to this area of active star formation, but is actually visibly offset. It's offset by a couple hundred parsecs, suggesting that the source is a relatively young source, but perhaps not as young as many theories would postulate. It certainly seems like the source is not from some kind of delayed channel of neutron stars merging together, but at the same time is not some just born in the last few tens of years ultra-magnetized neutron star. It's quite plausibly actually some type of interacting binary that could potentially be a few 100,000, if not 1 million years old or so. Now, I've alluded to this before. This is one of the nicest things that I have to show today, I think, is the CHIME telescope discovered a repeating fast radio burst source towards the famous M81 galaxy, this grand design spiral that covers a huge area of sky and is at a distance of only a few megaparsecs. This is the founder of our institute here in the Netherlands, Jan Oort, standing in front of an older picture of M81. Now, CHIME found this interesting source in the direction of M81. It would be a very, very nearby fast radio burst source compared to most fast radio bursts if it's only at a few megaparsecs. And we were lucky enough to be able to detect it using this VLBI network, detected a number of bursts and localized it to milli-arcsecond precision. And we're really incredibly surprised to see that the source is on top of a globular cluster, so a neighborhood of old stars, which is part of the M81 galactic system. So it's a globular cluster that has been known for decades to be a globular cluster associated with the M81 galaxy. And it was a huge shock to find a fast radio burst source in a globular cluster because, many lines of evidence lead to the idea that this must be some type of very young source, yet we're finding this source in this, kind of stellar graveyard of a globular cluster. One of our hypotheses is maybe that the source is indeed a magnetar, but a magnetar then formed through binary merger or through accretion-induced collapse in the cluster, because in the core of a globular cluster, the stellar densities are so large that you can have interactions between stars, you can have mergers, you can have mass transfer from one star to another. That's certainly a viable hypothesis, I think, but maybe this source is something completely entirely something different. Maybe it's some type of accreting neutron star or accreting black hole, and maybe the bursts that we're seeing are coming from a radio jet. So just a few other points that I want to make in the last 5 or 6 minutes to kind of bring this back towards what the SKA is going to offer. One of the other breakthroughs in the field of fast radio bursts in the last few years has been the discovery of an incredibly bright, like a mega-Jansky radio burst from a galactic magnetar, the galactic magnetar in 1935 plus 2154. And why is this important? Well, we saw a radio burst from this known galactic magnetar, so we know it's a magnetar because it's close by enough that we've been able to study it in detail. This radio burst was so bright that if this magnetar was in a nearby galaxy, we would have seen it still with our radio telescopes, and it would have looked very much like a fast radio burst. So this is one of the primary reasons why people say, a significant fraction of fast radio bursts must be coming from magnetars, because we've seen a fast radio burst-like event from a magnetar in our own galaxy just in the last couple of years. I argue that it's important for the SKA to be able to do high cadence observations at lower sensitivity, and I think this is a nice illustration of that point. So we followed up that source after this bright radio burst happened. We basically stared at this galactic magnetar for hundreds and hundreds of hours using very small European radio dishes that are part of the European VLBI network. So these are tiny telescopes compared to the SKA. And we stared at the source for, I think it was about 3 billion milliseconds. And we saw about 1.5 milliseconds of signal during those 3 billion milliseconds. So I think this really nicely illustrates that our ability to probe very rare astrophysical events is not always sensitivity limited. It's limited by how much on-sky time we can spend. And I think there's a lot of valuable science that one can do if you think creatively about how you can use an infrastructure like the SKA, not just to do the very deep, high sensitivity, high precision observations that it was originally built for, but also for doing high cadence observations, where being on sky and searching through, hundreds of hours of data make the difference. Because what's quite interesting about this additional detection of more bursts from the source is the fact that, coming back to this transient phase space that I was showing you early in the talk, we have the pulsars here, we have the fast radio bursts here. We've now seen radio bursts from this galactic magnetar that actually span 7 orders of magnitude in terms of their luminosity, and they really bridge from the pulsars all the way up to the fast radio bursts. So by being able to do these low sensitivity, high cadence observations, I think we've come to the conclusion that this known neutron star, known magnetar in our own galaxy, it can produce radio bursts that can be as weak as pulsars and as bright as the dimmest fast radio bursts. And you could ask yourself the question, at what point does the emission stop being fast radio burst-like and start becoming pulsar-like, or vice versa? But it's basically demonstrated that a single neutron star can produce a wide range of luminosities, wide range of phenomena, and provides a very plausible link between these two populations. And I don't have time to go into detail about it now, but in our group here in Amsterdam, we've really been trying to fill in this parameter space, looking at timescales of milliseconds, microseconds, nanoseconds. We've been looking at fast radio burst sources and trying to really fill in this parameter space and understand, what types of astrophysical events and sources exist, not only on these ranges of luminosities, but also on these huge orders of magnitude ranges in timescale as well. So maybe just one other quick point before I start concluding. I think SKA low, as I mentioned before, is also going to be an very interesting transient machine. SKA low has gotten a lot of attention in terms of searching for galactic radio pulsars, and I think it's going to be a fantastic discovery machine for galactic radio pulsars. I would argue that it's actually also going to be a very interesting FRB discovery and study machine as well. And that's because just in the last year, we've been able to discover the first bursts from a fast radio bursts that are visible at low far frequencies, and also visible, at SKA low type frequencies. And this is interesting because these very low frequencies allow you to probe the local environment even more precisely. Here are some examples of those bursts. And I think we've really just scratched the surface of this area of the parameter space, where we're talking about, pushing in the dimension of not, time scale or luminosity or on-sky time. We're talking about pushing in the dimension of radio frequency. And I think we know very little about coherent radio transients that could be very steep spectrum and be very well detected with SK low. So in conclusion, I'd like to say that I think this is a very exciting time for transient radio astronomy. I've been in the field long enough to have witnessed the early promises about how interesting it was going to be, and it took many years for people to start discovering interesting radio transients. But I think we're very much in the regime now where we are getting a lot of traction and making some very serious scientific discoveries through radio observations of transients. And to put this into context, the parameter space in terms of, in this case, field of view and sensitivity that we've probed up to this time with systems like the Parkes multibeam system and the CHIME telescope that I mentioned, is really quite restricted. And we talk about, SKA type sensitivities over large fields of view. The parameter space for new discoveries is enormous. So it would be shocking if there aren't other FRB-like type signals out there that are still to be discovered, given the large sensitivity of the SKA and its wide field of view. And I would say, other dimensions of parameter space that are going to be interesting to investigate are really the range of radio frequencies. So using both SKA mid and SKA low to search for short duration radio transients, both on very short timescales, which will be possible using the non-imaging modes of the Square Kilometre Array, but also on conversely on long timescales. So looking for radio transients with durations of like 1 second or just a few seconds. That area of the parameter space is very, very poorly explored, because whereas we've been searching for decades for radio pulsars on millisecond timescales, very few searches have been done on timescales of hundreds of milliseconds or seconds or tens of seconds, and there must be a whole host of astrophysical transient phenomena out there to be discovered still. So thank you very much. I mean, in conclusion, I think the future for transient science in general with the SKA is very bright. I focused mostly on fast radio bursts because I wanted to go deep on at least one topic. The high event rate, the fact that radio is an exceptional probe of intervening material. I think it means that the longevity of this field is really secured. So thank you very much, and yeah, Teresa, I'll pass it over to you if you want to handle the questions or host the questions.
Okay, thank you very much, Jason, for this wonderful talk. And yeah, now the talk is open for questions, comments. Please raise your hand, and Teresa will manage for all this section. Please, Teresa.
Okay. Hi, Jason. I think it's very nice to see you in person, and thank you so much for such an awesome talk. And I just wanted to say that as I was preparing Jason's proposal for his colloquium, this is a topic, his topic is very far from my own research, but very close to my SKA work here at the IAA. So I got really excited to hear from him to speak about this topic and how the SKA will be of benefit for it. So I also was hoping to hear a fair amount on FRBs, because it's an area I got interested in after writing some outreach article on it, and I definitely was not disappointed, and I don't think anyone else was either. Great talk. And I'm also quite excited that we share Canada as our country of doctoral studies. So is it possible for me as leading this to start up with 2 questions and be so bold?
As you want, Teresa.
Okay, first one is very important. I was wondering, that plot that ended up as an album cover, apart from the honor being involved with that, did you get any other credit? And
I did not.
No?
No, I don't think they even said where it came from, actually. It's a little bit less famous than the Joy Division album cover that is pulsar based, but I received no royalties of any kind.
Was the music any good at least?
No, the music was terrible as well, so that made me feel better about it, actually.
Okay, so it wasn't bad. Okay, so my other question is a bit of a broad question aimed for you as a co-chair of the SKA working group. Because of my work, I'm always very interested in synergy opportunities. So I was wondering, how might SKA transient observations be useful for other areas of SKA research? And opposite, how can the data from other areas possibly be used for transient research work? And so what specific areas can mainly be benefiting from or be of benefit for these data? Yeah,
I think the most obvious answer is first how we can benefit from other people's data, because I think the transient science in some respects is really driven by exploring new parameter space, and hence having access to the maximum possible data set. So doing commensal transient searches on every bit of SKA data that's taken primarily for other science, like H1 observations looking at gas and galaxies, we will benefit quite a bit from that, because it's a hard sell to say, give us thousands of hours of telescope time, maybe we'll find something, maybe we won't. But if we can do that for free, and someone else is motivated, we need thousands of hours to look at these galaxies, then that'll work. But how do we pay them back for that opportunity? I would say, I think as we explore the data on second timescales, we're going to be finding artifacts in the data and in the calibration of the data that are going to be creating false positives for us, and that could be potentially interesting for people who are looking on longer timescales and just trying to make accurate images, because it could also have effects on the image quality, the accuracy for those other science cases as well.
Okay, thank you. If you close the sharing the screen, maybe we can see everyone.
Oh yeah, sure. I'd be happy to stop sharing. Yeah.
And then I can see whose hands are up. Okay, I see Anton.
Hi, Jason. How are you?
Hi.
It was a very nice talk and a very beautiful presentation, by the way. And really thanks a lot. And in fact, we have seen a lot of new results with exciting science in all of them. Then really, thanks a lot. I have a lot of questions, but let me ask you just one. It's about the result of the repeating FRB towards M81, the one that is on top of the global cluster. First, some details. You said that this is a repeating FRB, which is the typical duration of each period of activity.
Yeah, that's a great question. We have some indications that maybe the activity will be going up and down periodically. There is one repeating source where we see that quite clearly at a period of 16 days. And I think that source could very potentially be a high mass binary system. In this case, we don't have a periodicity, but we very clearly see that the activity goes up and down. I mean, sometimes we'll observe for tens of hours, see nothing, and then we'll observe for half an hour and get 40 bursts from the source. And the last thing I'll say about the source, I didn't have time to present everything, obviously, but one of my students published a paper yesterday where she showed that these bursts can be as narrow as about 60 nanoseconds or so. So again, this shows that, you know, by probing in different timescales as well, that there's probably a lot of transient phenomena out there that we're just currently blind to in our standard observations.
Mm-hmm. And what about the image? And the image you have shown, the one that permits a very precise localization. Can you give some details about the total observing time for this image and things like that?
Yeah, so what we do is we do continuum observations over the course of hours. So we can make, you know, a continuum map of the field to see if there's any persistent radio emission, and we do that on timescales of hours or so. And there are a few repeating sources where there is actually a radio source at the same position as well, which we think might be some kind of very extreme nebula around the source. In this case, we don't see that. But then we take the individual bursts, where each burst is lasting for only like a fraction of a millisecond in this case. And then what we do is we produce a gate of the visibilities at each one of those burst times. So the total like integration time is literally just a few milliseconds or so. Yeah, but during that millisecond, it's the brightest source in the field for that 1 millisecond. And unfortunately, we have those bursts at different times during the observation. So the Earth is rotated. So we have good UV coverage then, or better UV coverage, because we can link different bursts detected at different times together.
Okay, thanks a lot. And I hope to see you in person again very soon.
Yeah, me too. Nice seeing you.
Okay, next up is Rainer.
Yeah, hi. Yeah, very nice talk. I enjoyed it a lot. Learning stuff, it's not my field. So did you just say 16 nanoseconds, Jason?
16 nanoseconds, yeah.
That's a few meters.
Yeah, that's right. So why is that scientifically interesting?
Boosted or Doppler boosted, there must be some extreme relativistic effect at play here. I mean, with a few meters, you can't get these energies.
Yeah, so there is probably some length contraction, time dilation effects to take into account as well. We don't know what the Lorentz factor is. We see the same from the Crab pulsar in our own galaxy. It can actually produce giant pulses that are even shorter than a nanosecond.
Bloody hell.
Yeah, exactly. And then, that's, the size of a football, right? And, so why was this scientifically important? This is scientifically important because there's a class of models that say FRBs are happening in the magnetosphere of a neutron star. And there are models that say the neutron star creates some explosion and then it creates a shock much further out where the fast radio bursts are being generated. And what we've argued is that it seems more natural that the bursts are being produced close to the neutron star because the emitting region needs to be so small to explain these very short timescales compared to much further out in a shock, which is much larger and where it's harder to explain why would it only last for 60 nanoseconds or so.
Thank you.
Yeah, you're welcome.
Any more questions? Isabel.
Thanks a lot, Jason. It has been great. It's not my field of expertise either, so that's great to learn a lot of things. I have a question just concerning maybe terminology, because you're talking about the transient sky. So you, as far as I've understood, you mean less than 1 second?
Not necessarily. Right? No, not necessarily. I think there's interesting transient signs to be done by looking at catalogs that span decades.
because I work in the field of AGN, so I was thinking about all the work we have been done in AGN variability, mainly using X-ray data. So it should be great to have the aid of radio frequencies to try to understand how AGN vary. But as far as the SKA is concerned, and the data that is needed, I don't know if there is any kind of approach that will consider those kind of objects in which the variability is taking its much longer period.
Yeah, definitely. Well, there's certainly going to be fields that are observed over and over again where it will be possible to create light curves for sources that are more, I would say, variable than transient. And you want to do that over timescales of decades eventually, right? And there has been monitoring of AGN done, right, with small radio dishes, and there are databases of thousands and thousands of AGNs where for decades and decades you have the radio brightness as a function of time.
Thank you, and again, it'll be a pleasure for us to have you here.
Yeah, I'm looking forward to visiting. Yeah.
Okay, do we have any more questions? We're all just excited about what we just heard here, and no, I don't see anything. We're back to you, René, then.
So, okay, thank you, Teresa. And just for closing the talk, thank you, Jason, again. Hope to see you here in October. And thank you very much for the talk.
Yeah, thank you very much for inviting me. It was fun. Okay, take care, everyone.
Okay, let's stop recording, so we are off the record.
Okay. Okay, good. Yeah. Yeah, thank you very much.